I see. All right. Hello, everybody. My name is Seth Schweitzer from Cornell University in the USA. I'm going to be talking about using infrared imagery for surface velocimetry. We call this method IRQIV for infrared quantitative image velocimetry. So there's no particles, so it's not particle image velocimetry, but there's a lot of similarities. I'll give an overview of the method, show some results for measurements we've made, and talk about a few of the applications that we've been using it for. And I'm just going to point out two recent publications that cover most of what I'm going to be talking about today, if anyone's interested in more details. So first step in our process is image acquisition. This is similar to what people do with a fixed camera for LSPIVs. We find someplace high up to mount a camera. The main difference between this and using visible light imagery is just the type of camera we use. These are very highly sensitive thermal infrared cameras. They are sensitive enough to capture temperature differences on the range of 0.1 C or Kelvin or lower than that even. But the trade-off is that the sensors inside of them have to be cooled down to very low temperatures for them to operate, which means additional cost, additional size, additional power demands. But these are the images that we get with them. So these are two separate sites that we've measured at. There's a picture of the setup at the bottom. I've used different color schemes for both of these images, but it doesn't really signify anything. In both of these, what you see in the center is the water surface, and everything sort of around the edges you can make out from these pictures below. And what we're seeing at the surface there is very slight temperature differences that are generated by a combination of heat exchange at the water surface and turbulence generated at the bottom of the channel. So in general, the bulk water has fairly uniform temperature. The air above it has fairly uniform temperature, but those two temperatures are not the same. There's heat exchange happening at the interface. And even though that heat exchange itself is probably spatially relatively uniform, what is not uniform is the rate at which water near the surface is being replaced by bulk water from below. So we have water near the surface that has lost or gained heat, and it's being replenished from below, from the bulk, at a rate that depends on the local turbulent events. And we see expressions of those turbulent events on the surface. And I'll show a video in a second. We are going to track the motion of those features in space and time. So this is a video of what it looks like. This I'll point out just that this is accelerated. It's playing about twice as fast as the actual speed. And you can see, first of all, that everything is advecting at the mean velocity of the flow. But if you kind of look carefully at any of those eddies that you can see advecting by, you can watch them evolve over time. And from a practical standpoint, just as far as velocity measurements, I just want to point out how we have this rich texture everywhere in the image from riverbank to riverbank. This means that we can make continuous measurements really at any location without any need to add seeding or to add any kind of illumination, because the signal that we're tracking is emitted by the water itself. It's not a reflection from an external light source. So this allows us to make continuous measurements over the entire field of view, and it allows us to do it at very high resolution without needing averaging, which means that we can capture instantaneous velocities and calculate metrics of turbulence. So at this point, we've acquired our images, and then moving forward, the analysis is similar to other image-based methods. We first perform pattern matching, pattern tracking in pixel space. We use the minimum quadratic difference method, which is an alternative to cross-correlation, which is often used. We find it to be more robust for these images that have a range of intensities. Cross-correlation methods sometimes are confused by regions of high pixel intensity. And once we've done our pattern tracking in space, then what's left is georeferencing. So we follow Holland et al.'s method. We separate our georeferencing into two steps. First, in the lab, we do an intrinsic calibration. We characterize any distortion in the optical path and correct for radial distortion or other characteristics of the camera. And then in the field, we do an extrinsic calibration using GCPs. So this is done to let us identify the exact location and orientation of the camera. We use those two calibrations to calculate a georeferencing transformation. And then that transformation plus knowledge of the water surface elevation lets us transform the displacements that we found in pixel space to both their location in XYZ and a velocity in XYZ as we track them over time. So I'm just going to point out that we do our pattern tracking in pixel space, and we only apply the georeferencing after the fact. We do not rectify our images before performing image tracking. As a comment on georeferencing, we've developed a tool that helps us analyze uncertainty in georeferencing. Essentially, we use a Monte Carlo simulation. So if we have our calculation, which takes, if we're using GCPs as inputs, it takes the locations of the GCPs in pixel coordinates and in surveyed coordinates, XYZ. We perturb those inputs by some small amount and run the calculation again. We repeat this many times with a range of different perturbations to each of the inputs, and that gives us some kind of sensitivity analysis on the output. How does the output change with these changes to the input? This method it has been made publicly available. It's also set up to analyze uncertainty from direct georeferencing, meaning cases where instead of using GCPs, we have knowledge of the camera's location and orientation from some other source, such as the IMU that was discussed earlier with Hydro STIV, or if it's a drone input or anything like that. Okay, so to show some results. So this is a transect of the mean velocity all the way across the river at a site in California. You can see how we capture the boundary layer effects on the side here. At the far side of the river here, if you can see that the boundary layer appears kind of truncated. That's because of occlusions of a tree here. So the velocity measurements are valid here, but at some point the method is just seeing trees instead of water. So we're not capturing the full boundary effect here. But of course, this transect is just at locations that I've chosen to analyze and plot here for clarity, but we could measure a velocity at any location within the field of view. So here I'm plotting only about from the riverbank about halfway out to sort of zoom in and get a better spatial scale. But what we have in the background is the mean velocity magnitude, and then we have vectors plotted over it. So of course this is a straight channel. Nothing very interesting is happening in the mean velocity field. But if we go ahead and then take the instantaneous velocity at each point and subtract from it the mean, then we get something that looks like this. So this is an animation at the same site. These are instantaneous velocities. So the pseudo color that you see in the background is the instantaneous velocity at each location. And the vectors are the difference between that instantaneous velocity and the mean velocity at that point. And this just shows very clearly all the richness of the complexity of the velocity field that we can capture here. You can see exchange of momentum in and out of the boundary layer. You can see vorticity passing by. And the main application that we've been using this kind of method for is fish behavior studies, where it's important for us to be able to correlate what the hydrodynamics were doing at a particular time with what kind of fish behavior we were seeing at that time. And I'll talk a little bit about that when I show some applications. But first, hopefully to convince you that these measurements are accurate, this is a comparison of a velocity record time series measured by QIV and measured by an ADV at a nearby location. So this is a time series just at one location on the surface compared to an ADV about a meter or so below the surface nearby. These measurements are not made at exactly the same location. They're not measuring the same velocity, since the IRQIV at the surface has a two-dimensional velocity field. The ADV is a three-dimensional velocity field. So they are not identical, and we don't expect them to be identical. But you can see that the same major features of the flow are captured in both methods. So that gives us a good feeling. And if we look a little bit more rigorously at statistics of instantaneous velocities, then we can see, so first I'll say that the coordinate system here is rotated such that U is in the mean, along the mean component of velocity for each of these fields. So V bar, by definition, the crosswise velocity is 0. So we can see good agreement in the U direction. If we look at the RMS fluctuations, turbulent fluctuations, then there's not the same value for U prime RMS and the ADV and IRQIV, but importantly, there is no vertical velocity in the surface measurement because it's at the surface. And if we look at our total turbulence kinetic energy, then it's recovered. So this gives us confidence that we're measuring the same flow with these two instruments and getting good agreement. Okay, so some applications that we've been using this for. I'll talk about two projects. Evan has a talk later today and describe an additional project that our lab is involved with. But this is work that we've been doing with the California Department of Water Resources. And the main motivation here is a fisheries management issue. So we're working in the Sacramento-San Joaquin Delta. So these are two major rivers that flow into the San Francisco Bay. And this is a very complex system hydrodynamically, because in addition to the fact that this whole system is tidally forced, so there's flow reversal even quite a distance upstream, there's also a lot of human interference. There's diversions of water for irrigation, there's diversions of water for salinity control. There is a massive amount of water that's pumped out of this system to Southern California, to Los Angeles and other locations. And from a fisheries perspective, the issue is that there are salmon and other fish that want to swim upstream, spawn in the headwaters of the river, and then juvenile fish need to be able to navigate their way out to the ocean quickly without meandering through the system too much and basically reducing their survivability rates. So one of the things that the state is doing to improve survivability of these fish is identifying locations along the path where a simple navigational choice, right or left, can have a very large impact on survivability rates. And one of those locations is somewhere called Georgiana Slough. So this is a branch off of the Sacramento River. This is the main Sacramento River. And if fish migrate down the Sacramento River, they'll be following the track they should be. But if they turn and go down Georgiana Slough, then their mortality rates increase. And what the state is doing there now is constructing a BAF, a bioacoustic fish fence. So this is along this distance of, this is a couple hundred meters. There will be pilings installed at fixed distances, and between them a system that has bubblers, flashing lights, noise, different elements like that are supposed to deter fish from wanting to navigate down this way. So, of course, to be able to measure how well this is working, there are large-scale experiments planned. These involve releasing thousands of fish and then tracking how they behave as they transit through this part of the river. The scale of this is very large. These are thousands of fish. They need to be hatched, transported here on a certain schedule. They're surgically implanted with a tracker to be able to, an acoustic tracker to track their path through here. And of course, fish are, their behaviors are dependent on the environment they sense around them. So accurate velocity measurements are important here. But among other things, because of all of these bubbles and so on, there's concerns with making measurements with ADCPs. So we'll be installing infrared, at least one infrared camera here to measure in this area. And that this will be likely installed on a piling and sort of in a fairly autonomous kind of installation. And one other site that we're working on, sort of a similar kind of use, is the Fish Pass facility in Traverse City, Michigan. This is a project of the Great Lakes Fisheries Commission, the GLFC. So this is a facility that has not yet been built. It's slated for construction to start in the immediate months. And the issue here is locally in the city of Traverse City, there's a dam that is reaching its end of life and needs to be replaced. But on a larger scale, in the Great Lakes Basin, they've identified more than 250,000 different flow obstructions of a range of sizes that impede movement of species in the rivers, and many of them are reaching a point where they would need to be replaced for infrastructure reasons, and they also possibly should be removed or replaced for our current understanding of ecological management compared to when they were built. But the issue is, if we remove these barriers, then we will be allowing invasive species to get to locations where up till now they've been blocked. So the goal of Fish Pass is to, at this site of the Union Street Dam, not just replace a dam with a newer dam, but to first install this outdoor laboratory. So this is a 10-year project, multi-agency, multi-million-dollar budget, where the goal here is to, at the first step, there's these fish sorting channels, and a range of technologies will be tested out here to see how they can reach, hopefully, 100% exclusion of undesirable species passing through here. And a lot of it is based on the hydrodynamics right at the entrance to this system. So again, this is a place where IRQIV will be made use of. And for this kind of measurement, it's important to be able to measure continuously for periods of days or weeks or months, potentially not analyzing all of the data, but depending on when biologists identify a period of interest, we need to be able to go back to any point in history and get high resolution measurements. So we need something that can measure in high resolution over a high spatial area continuously for extended periods. So with that, I want to acknowledge our major funding parties. That's the California Department of Water Resources and the Great Lakes Fishery Commission, and say thank you to two camera manufacturers, Teleops and Infratect, who graciously loaned us cameras to try out for some of this work. And I will leave you with this animation of the water surface in IR and take any questions. Thank you.
That's great, Seth. Thanks very much for a very interesting presentation. Any questions from the audience?
Yeah. Do you get any interference from the atmosphere? That can be like water, hot air, something that can affect the measurements?
So on the scale of distances that we're operating at, which is on the order of tens of meters, I wouldn't say that that you see. I mean, you wouldn't see the air temperature necessarily affecting anything. Of course, if there's rain in the way or fog, that can be something of an issue. But I think similar to most optical methods that people have been talking about here, the main issue is once atmospheric conditions start affecting the water surface. So rain might not be that much of an issue as far as being able to see the surface, but if it's disrupting the surface itself, then that could be an issue. What we do have as far as environmental is if there are a lot of objects in the area of the water flow, whether it's buildings or trees or anything like that, that are giving off their own heat signature, that can be reflected off of the surface of the water. If you look closely, you can see a couple of artifacts related to that in this video. But the usual tricks, subtracting mean images and things like that, work here pretty well to address that type of problem.
Seth, just a bit added on to that is, do you get any sort of seasonal effects, like with different levels of humidity over the water surface?
Yeah, so that's a really good point. So The quality of the image, or for the purposes of velocimetry, mostly has to do with how much heterogeneity is there at the surface. So how much texture do we see there to that we can track, and the greater the difference between air and water temperature, the better a signal we'll have, and humidity definitely plays a big part of that. So the metric we look at is the difference between water temperature and wet bulb air temperature, which incorporates humidity. And of course, this we haven't measured in Michigan in the winter, but aside from ice, one can expect that the air-water temperature difference might not be particularly large, so that might present some other challenges.
Okay. Any other questions? Okay. One more question, Seth. Haven't escaped yet.
That's a couple of questions, actually. I was just interested to know how much one of those cameras costs, and also the images I've seen, it looks like your camera's mounted quite high. How does angle come into?
Yeah, so the cost, they're expensive. Depends on the resolution. Something on the order of 1 megapixel is less than $100,000, but getting close to $100,000. There are cameras that are closer to, I guess, what we used to call VGA, so 480 by 512 or 640, something like that, pixels, maybe sub $50,000. And then there are higher end detectors that there's a 2 megapixel camera that goes for around 250, I think. As far as the angle, so yeah, I mean, like any optical method, the higher up you are, the closer you are to a normal view, the better your imagery is going to be. Part of I mean, this is not unique to infrared, but when we get low, what we start running into as much as anything else is that reflections become more dominant. So one thing that I guess is a little different maybe in the infrared is we're looking at a signal that's emitted by the water, and it's a function of the temperature of the water, but also the emissivity. That emissivity changes as a function of the viewing angle. So when you get to very shallow viewing angles, really what it means is that your reflections will be much stronger than the signal emitted by the water.
Any other questions? More questions, Seth? Thank you very much for your presentation. Really quite interesting. So thanks very much.
Okay, thank you, everybody.
Next speaker is Carlo.
Yeah.
So do Nick talking about even further away imaging, I think.
Slightly further away. Sorry. Share screen again. Okay. Okay, so I'm Nick Everard from UKCEH, in case anyone had forgotten, and this time I'm talking about our FluViSat satellite velocimetry project. Next slide. So yeah, this is, first off, is an international project, so we're collaborating quite widely. So these are the people involved in my organisation, but we're also working with Mark Randall. Where is he? There he is, from Queensland, and Dr. Guy Schumann from RSS Hydro Luxembourg, who's more of a specialist in Earth observation techniques, previously worked at NASA. Our funding, I must recognise, has come from the European Space Agency very generously. And the imagery is from Planet Labs. So you may have seen their high resolution imagery when there are natural disasters, perhaps also in the case of the Ukraine conflict, some of the imagery there comes from Planet Labs as well. Next slide, please. What we're trying to do here is we're trying to see whether we can do velocimetry using video from space. Perhaps that's the key thing to convey that. So why are we trying to do this? I mean, you all kind of know this, but floods are the key application. They're a big problem. They're getting worse, and they're difficult to measure. Next slide. So this is an example of the kind of problems that we're facing. This is Bozkurt in Turkey in August of 2021. Just an incredible flood, which if you try and think about trying to measure that with any established methods, you're not going to succeed. So these are the kind of conditions we're thinking of. Next slide. So yeah, and to look a bit more closely at that, globally, monitoring networks are often inadequate and frequently, surprisingly, to me anyway, in decline, even at this stage in our civilization. Monitoring infrastructure is costly and can be damaged by floods. What you can see here is a gauging station in the northwest, well, not very far from here, in the northwest of England, that was badly damaged by Storm Desmond in 2015. So there was a cableway across the river, and the other problem here, most of the flow was actually going around the back of the hut during the flood. So yeah, enormous bypassing. And this is another one from the same flood event, also within about 50 miles of here. You can see enormous erosion of the bank on the far side. And if I'd got the whole of the picture there, the hut was about to fall in the rim. The bank had been eroded away by about 5 meters. So yeah, really destructive. Yeah, next slide. So what are we trying to do? So the FluViSat project, the name stands for fluvial video from satellite. So that's kind of the name. And we're trying to use very high resolution satellite video to measure stream flow from space. So the video, it's nominally a 50 centimeter pixel size, and they can shoot a 30-second burst of video. And this is Planet's SkySat constellation. There's 21 of these satellites, so they can get to a lot of places. And significantly, I mean, I've been reading about people trying to measure stream flow from space for quite a few years, but this is a direct measurement of water speed. Most of the Earth observation for stream flow measurements are actually just altimetry. They're looking at big pixel sizes, they're looking at surface elevation changes, and it works on things like the Amazon, but not really at smaller scale. So, okay. So some of the benefits of our project, we think, or of the solution, if it works out, allows stream flow measurements on large, medium and large rivers, pretty much anywhere in the world. So the SkySats can image any place on the planet. No people or equipment are needed on site, even in the same continent. Just request the video is captured, it's sent to you, you can process it. Multiple daily repeats, because there are 21 satellites in the SkySat constellation, and they claim anything up to 7 revisits in the same day. We've had 4 videos captured within 23 hours on the River Tweed, close to here. So sort of kind of proving that that's not just marketing hot air. Validation and real-time training of global hydrological models, we think could be an application of this. And we're interested to see whether we can get topographic data from the imagery itself to start building up a sort of DEM to run the velocimetry through. And finally, and not least significantly, it's kind of cool, and it's kind of a headline thing for how hydrometry is progressing. We've gone from little propellers in rivers to using video from space. I think is kind of exciting. Next slide. And yeah, I have to give credit to Mark, because it was his idea originally. He told me about this possibility 5 or 6 years ago. We said, right, we must do something about this, and it's taken up to now to get to this point. And I think that's largely because Planet is a commercial company. You know, they'll tell you that they're doing all sorts of stuff for the benefit of the planet, which I'm sure they are, but ultimately they have bills to pay. You know, they are a commercial enterprise. So it was getting the relationship built with them and then getting the ESA funding that kind of unlocked this. But it was Mark's idea originally. Credit to Mark. Okay, so we're using the HydroStiff software. You've seen it several times already today. We're using it. Oh, this is a video. I forgot that was video. So what we're doing, it's probably already been explained, but we're tracking brightness along these blue lines to generate the red line is the vector. So I think you can see, you know, quite clearly you'd be able to see the movement of this feature down the line. What we end up with then by layering these things up is these slopes, and the angle of the slope gives us velocity, and it's nice and robust. Okay. I've been working on my slides this afternoon to add to this comment here that, yeah, this is an example of what I think Alex was talking about earlier on, that the velocity is varying quite significantly along these searchlines because we've got this strong converging flow here. We've got a very different velocity up here to what we had down here. Up here, it was something like 4 meters a second. Down here, it was pretty much nothing. So when we're going to look at some of the images of that in a second, but yeah, and then very varied. I mean, this is a tidal flow. This is a tidal flow that goes in and out of a Scottish sea lock. Twice a day, you get this colossal flow of water, and it all funnels under a bridge. You'll see a picture of that in a minute. But you get this very, very turbulent and complex kind of flow pattern. But it does a nice job of resolving it. Next slide. So here's our validation concept. We wanted to try and validate this. So we came up with the concept that unfortunately the satellite is almost obscured at the top there, but there's the satellite. It has a relatively large footprint for satellites. It's not that big. It's about 1.3 kilometers by about 800 meters. So it's not that big, but it's a lot bigger than we can get from the drone. So yeah, we're going to use the drone for comparison velocimetry. And then where possible, and actually at this site, this is the site I was just talking about, we didn't deploy the ADCP because we would have lost it. The flows were too strong and the body of water was too large. We had hoped maybe to be able to go and measure this with a RIB, rigid inflatable boat, but we weren't able to in the end. So at this site, it was just the satellite video compared to the drone video. But where possible, we've also compared to ADCP data. And so here's kind of how we're doing that. So this is the River Tay in Scotland. So we've got the ADCP transect, which is going to give us the velocity profile, and it's going to give us the cross section. And so we use that where we've got it, and we've got it from our ARC boat, or in Mark's case with a crewed boat, a manned boat. Okay. This is a video of one of the. This is actually one of the videos of it will play. So just to give you an idea of the quality of the video. This is shot from 450 kilometers above the Earth by a satellite traveling at 27,000 kilometers an hour. So what we notice, you notice it wanders a little bit. So we've had to deal with that wandering. But the other thing is because the satellite is traveling so fast, for 30 seconds it can image one location, but its viewpoint relative to that location is changing. So there's actually quite a lot of distortion and morphing of the imagery within that as well. But it's pretty nice. Can you play it again? Want to play again? Yeah. You can notice things like there's a little car trundling along the road here, or several actually, there's 3. And down here you can actually see the structure of the surface just a little bit. We hoped for big flows. We didn't have big flows. It was a really dry winter. So this is the River Spey. In a flood, you'd have 300, 400, 500 cubic meters a second. We had 60. So we think if we had a flood, you would see a lot more of the structure and the surface of the river. Next one, please. So does it work? We asked the question, and yes, I've given you the answer straight away. Credit to Mark. This is one of Mark's. This is the first one. So appropriate enough, Mark was able to test this out first of all. So what we've plotted up here, nice and visually, are the velocimetry from the drone and velocimetry from satellite. So you can see a very similar shape. If you could read them, you could see very similar velocities are calculated there. But most importantly, discharge calculated from the drone, 1,052 cubic meters a second. Discharge calculated from the satellite, 1,048. So I mean, you couldn't get a cigarette paper between the two. So that's an excellent result with any technology. So for a first go using imagery shot from space, we were pretty much blown away. Next one. So yeah, it's come out a little bit dark, but this is the Falls of Laura. This is that complex flow coming underneath the bridge. Again, you can see very, very similar patterns. We had the added complexity here of it being tidal. You know, the tide comes and goes very quickly, twice a day. So synchronization, you know, with best will in the world, we couldn't actually get our data at exactly the same time as the satellite, which added some complexity to that. And that's partly why I haven't actually shown the velocities there, because the different tides did generate different velocities. Okay. But here are some of those velocities just to give you an idea. And notice things like the distinctive shape out here, but also that we get some very small negative velocities over here. And the next slide is from the drone. So it's rotated a little bit around, but you notice over this side, we've got those negative velocities again, and that same sort of distinctive shape in the middle. The highest velocity in that case from the satellite one was 4.4, I think, 4.3, 4.4. We got about 4.8 here. But this was a different tide on a different day. So we're pretty happy that we've got good results there. Yeah, here's that complex flow. So you can see, I mean, this area here was very, very fast. This was one of the fastest areas, but it was very smooth surface. It was relatively hard to resolve something from there. Out here, we had very, very turbulent flows. Over here, it was actually going backwards. Here, we had great big sort of turbulent eddies coming through. You can see it was a great big mess of flows. Here, there's a little jet that comes around the back here. People were kayaking through this whilst we were there, crazy people. Okay, next one. So when we look at some of the search lines, so anyone who's ever used HydroStim will be aware that when you do this analysis, we showed you those kind of slopey lines. for reasons I don't fully understand, when I process this, I get these they're not sort of square boxes where it's easy to see the angle. I get more of these sort of sticks. But within them, if you look at these ones here, it's pretty clear the lines running through them. So the analysis is pretty robust. But I think if these things came out slightly more square, or we could reshape them, it would be easier to judge that angle. So I don't fully understand that. But anyway, the point is you can clearly see the velocities that are represented by these lines. Okay. So yeah, here we look at some of the complexity in this. So this is one I've tried to point out from where across the section these came from. So here, it doesn't really come out terribly clearly, but here, because there's not a lot to see here, you can't see it. If you were looking on a computer screen, you could probably see it. But here, the direction of flow is like this, but then it goes like that. So in other words, in this case, that's the speed of flow. So we've got a very high velocity here and then a low velocity there. So I tried to represent that manually by drawing some lines into this section and drawing some lines into this section. And I drew 3 in this section and 2 in that section because it's a relative proportion of the area or the length of the lines. Out in the middle, it was pretty easy, pretty unambiguous. Over here, very turbulent and messy. So the hydrostick usually did a nice job, but sometimes I tweaked it just a little bit. But you know, when you're looking off the bridge at this, it was all kind of churning around in every kind of direction. So does it work on use case scale rivers? So that was a tidal flow. We chose it because it was so big, because we knew when we'd have a big flow coming through there. This is the River Tweed at Norham. This is where they got us 4 videos in 23 hours. This is a drone image taken of the river on the day that they captured their video. Can you see any surface features on that? I mean, even when we did a nadir view and we came to process it, we did get good results, but really you couldn't see very much. So we really didn't have high hopes for this. However, so what actually happened was, this is a whole learning process. This is the first time we captured imagery in the UK. We'd given Planet the area of interest that we wanted them to capture. We understood the footprint of satellite. So we confined our activities to this sort of blue box here, because this is what we thought they were going to image with the satellite. In fact, the imagery extended, well, this is the image, the background black and white image is the image. So we got all of this as well. And to my amazement, we could actually see features on the water surface here and here. This is wind driven, so we weren't going to process that. And over here, this is wind driven, and this was wind driven as well. But here, it's more subtle, but there were features here that were moving with the flow. So all of our data was collected here, so we couldn't do a direct comparison. So we went back later on. So it was only after the fact we'd gone home and we got these videos, we processed it. So we went back to do some bathymetry mapping, so we could retrospectively calculate discharge based on the velocities that we got in, yeah, here's about where it was. And so we could work out the cross-sectional area. We'd got the surface velocity, we used the surface alpha, we could calculate discharge, which we could compare to the measurements that we made down here with our drone and our ADCP. And lo and behold, what did we get? We got 113.5, which was from the satellite, and we got 116 from the ADCP. So a really close result, within 3%. So crazy, really, crazily good. I mean, some of these vectors are probably wrong. These two at the edge are showing a negative velocity. I don't really believe that, but you generally see a trend towards higher velocities in the middle and lower velocities at the edge. But frankly, given the flow conditions we had and the surface features or the lack of, this is astonishingly good. And again, we had 115 is nothing like a high flow there. A high flow there is about 800. So we weren't gifted with a high flow. Okay. So yeah, just a few of the challenges we've experienced with this project. This one here, if you can figure it out, we've got the imagery for the first frame of the video and the last frame of the video represented by different colors. So over here, it's perhaps easiest to see. So this hedge line has sort of morphed from the orange position to the blue position. And you can see the same kind of thing over here. This road has switched from this position to this position. And that's because the satellite's view is changing. So everything sort of stretches and just morphs a bit. So we needed some quite advanced rectification to sort that out before we could process it, because these gross movements or apparent movements of shift of pixels, we're looking for tiny movements to represent the water speed. So, you know, to be seeing the hedge line move by sort of 50, 100 meters we've really got to precisely rectify that before we can see very small movements of water speed. Okay. We also found that with some of the stabilization routines, the imagery was degraded quite considerably. So the HydroStiff software does offer a stabilization routine, which is very nice. But actually, we lost almost all of the surface detail when we used that, so we couldn't process anymore. So this is the original. You can see these kind of little roughness features. It's very subtle. It's a bit fuzzy, but it's shot from space. But they've all disappeared pretty much here. So then they're stabilized by our project partners. You can still kind of see these features. So they're not quite as crisp, but you can still see them. So then the next question, as we set out on this project, we decided we wanted to do some sites where we could validate, but we also wanted to see if we could capture some extreme events around the world. So you're probably, I'm sure you're all aware of the flooding in Pakistan that happened this summer. So we tasked Planet with trying to capture some videos of the Pakistan flood, which they did. They got me 6 videos. Ooh, back it up one if you can. They got me 6 videos in the space of 10 days.
What?
Will it go back?
Oh yeah, press
Yeah.
play, but it just went ahead.
Oh, no, it wasn't the
Oh.
video. Sorry, it's just a still from a video. Easy mistake. Yeah, so this is just one of those videos. They got me 6 videos in the space of 10 days. This is the Indus River in Pakistan. Nice clear flow patterns on it. I was able to do with velocimetry in 3 locations. I could have done it in more. Pretty much anywhere along this reach, it would work. One thing we noticed, and this illustrates quite nicely, is as the satellite would whiz overhead, sometimes the illumination became very favorable and sometimes much less favorable. So I took this image, the background image from the start of the video, when the velocities were, when the surface features were very, very clear. By the time the video finished, when the satellite had changed its position, a lot of this detail had actually disappeared. But the HydroStiff software could still pick out enough to give us the results. But I think you can see that you could see the flow. Sorry, that was my fault. You can see the flow patterns. You can see this fast water coming around here. You can see it's then more uniform all the way across. Then it starts to hug this bank and even get some negative velocities over this side. So, it's really doing a nice job. Okay. I think I already mentioned this, but yeah, there's 21 satellites, so they can genuinely image any part of the planet multiple times a day. It's a quick one. Oh, we're on to the sort of closing stages here. So conclusions, good results for medium and large rivers. I think if you can measure a UK scale river, what we think is large is not large in the rest of the world. So that's pretty impressive. This rectification and stabilization, that's need improving. I think, we're getting good results, but I think that could be improved. Cloud cover is an issue. It just doesn't work if you've got clouds. So working on rivers in Scotland was challenging because they are usually covered in clouds. We're interested to see whether high resolution SAR could work. So that is synthetic aperture radar. Most SAR satellite imagery is large pixel sizes, but there's a company called ISI who have a whole constellation from which we make 25 centimeter pixel sizes. Most operators, I don't think, get as fine as 25 meters. And huge potential for direct application and for validation and training of hydrological models, we believe. And I think I have one more slide, which is an updated shot, Norris, just for Alex there. And it is a video. I think this one is a video. So this is the Fort Laura. This is that complex flow you see. And you see how much this is wandering. So we were able to process this one, but there's an awful lot sort of wandering around. But the camera has a focal length of 3.6 meters. If you've ever tried to sort of stabilize a camera with a zoom lens, and you think of 3.6 meters, it's not surprising, but it wanders a bit.
Okay, great, thanks, Nick. Absolutely different scale.
Is there time for a question, or did I waffle too much?
I did waffle a bit.
Daniel.
What's the price for the machine?
Oh, Daniel's asked, what does it cost for anybody online? So the videos are not, how can I put this? I mean, Planet might be listening in, I don't know. The videos are not that cheap, but considering what they are. But yeah, we were able to get a good deal for a sort of batch of videos, but of the ESA funding we received, quite a big chunk of it did have to go to purchasing the videos. But I should say the Pakistan videos, they captured free of charge for us, because I think they saw the sort of, the humanitarian need in that. So yeah, it currently is not that cheap. I think I'm politician. No, I couldn't remember if I put the slide in, but there is another method that we've been doing this, which I showed a slide this morning. So I showed it, which is, so these are videos. To do a video, you know, it's a 30-second thing. It occupies the satellite throughout that time, and we still don't know whether the whole satellite has to sort of pivot to look at the thing, or whether it's just the imager on it. But there's physical movement required of a thing up in space to do that. So Planet can also capture very high frame rate still imagery. And I was like, well, what's the difference? If I can capture 50 frames a second of still imagery, why isn't that a video? Well, the difference is it doesn't lock onto the target. So with this one, it locks on and it keeps looking. The still imagery, it just goes. And so the question was, and this challenge came from Planet themselves, could we actually measure velocity in rivers just using this? And we have 0.3 seconds between the first time the river is imaged and the last time it's imaged. So that's our time separation. And yeah, it works if the river's flowing fast enough. And by that, we mean sort of 3 meters a second and faster. It can work. And but my point coming back to cost is that's way cheaper. If we can make that work, it's way cheaper. Salvador was first.
Stabilization. You showed this figure that you showed is you try to stabilize that.
No, that's before stabilization. That's
why is it not moving just like why is it?
well, but because the thing, I mean, imagine this is my zoom lens, and something on the floor, this wedge of cheese is what I'm interested in. So I'm going, and I might not be going directly overhead, I might be going at an angle, but you know, there's just a lack of stability in the system. So I'm trying to lock onto that, but I'm probably sort of gently going, you know, as you would if you were holding a zoom. You know, I might try and take a nice video of Mike, but as I did that, you know, Mike would, you know, wander around.
Okay.
Is that a suitably visual explanation?
Yeah.
You sound skeptical, Sam.
Yeah. Anyway, so
Buy a 3.6 meter zoom lens. Try and focus on.
My follow-up question is like, so you said that there were issues that still improve the stabilization for camera. So I'm very surprised that you got small close results with the drone and the stabilized satellite video was like 0.1%, right?
We're very skilled hydrologists.
And that's that they also could SD.
I think the thing is, though, I mean, it's a video, right? And as long as you can scale it, you know, as long as you can see them. Can we play this one again?
Yeah.
I mean, unfortunately, it's not a great projector, but if you can see it on a laptop, you can so clearly see the movement here that as long as you've scaled it, why wouldn't it be right? And in a way, actually, with these complex turbulent flows, and I used longer search lines, although I did do shorter ones as well, but this dealt better with that complex flow almost than the drone did. Probably the drone had the drone video had too much detail that it you know, it could track all these different things, whereas this is sort of smudged away a little bit. But yeah, I mean, we were blown away. But logically, as long as you can see the flow, and as long as you can scale it, and as long as it's not, you know, if you can fix that stretching and morphing, then why wouldn't it work?
Also, the measurement are highly correlated because you use compare ADCP with imaging based on weighted area computed with the ADCP and depth surface depth of electricity computed from ADCP. So they are like highly correlated things. So it's great that it's like everything, but I think when you compare method, you also think about that. Especially for large rivers, most of the discharge is from the weighted area. Some for the velocity, so here you have common points, which is same weighted area, the same depth. You have to keep in mind the method. They do not explain that it's so well, and it's just exactly the same number. They explain that it's close. And very often when we compare image-based method and ADCP using the same bathymetry.
They work out very well. Yeah. But I think once we've got that cross-sectional area, then well, it would be interesting to do some repeat surveys of, if we can get repeat imagery, trouble is we spent our budget. So I mean, a lot of this has been actually working on this kind of relationship thing, and ESA, I think, are very keen because I don't think video from space ever found a market. So it's been available for some time, but I don't think it's ever found an application. So ESA really seem to like what we're doing because it provides a demonstration of the value of video from space.
Sure, it's got nice military applications.
Possibly, yeah. Right.
But could it be possible to have like a agreement, like if there are big floods, they will shoot the videos?
That's what we would like to try and
Yeah.
get to. Yeah. And there are arrangements, aren't there? I can't remember what it's called, disaster charter, I think it's called, but the satellite companies are supposed to, some of them have signed up to try and to do that sort of thing. But yeah, I think making it responsive enough is the challenge though. So that the Pakistan flood, by the time we'd gotten to agree to videos, it was pretty much sort of peaking on its way down, and that was a very long duration flood. So I think to get it so that we could say, hey, this
Like
flood is
flood forecast kind of thing,
predicted for next week.
and verifying the flood.
Yeah.
is,
Right.
yeah.
I think we'll have to move on with fire alarms, pockets and everything else. Go, down to one. Let's move on to our third talk this afternoon. Is it Evan?
Yeah.
Who's hopefully still with us.
Yeah.
Sorry.
Hello.
Sorry for the delay. As I say, we've had fire alarms and long coffee breaks here, I'm afraid.
No problem. All right.
Right. Yeah.
Is this showing up for everyone?
Yeah. So again,
Awesome.
infrared.
Right.
Image filter.
Sorry?
I'll let you start and get on with it if that's okay.
Sounds good. Thank you. Hi, everyone. Good afternoon. My name is Evan Heberlein. I'm a PhD student at Cornell University, advised by Professor Cowan, and I also work very closely with Dr. Seth Schweitzer. And today I'm going to be talking about our IRQIV method applied at a complex tidal flow through some coastal flood infrastructure. So honestly, a good segue from Nick's talk. So this study site that we just started at in July is on Cape Cod, which is in the northeastern US in the state of Massachusetts. So this arrow is pointing at Cape Cod. It's this large peninsula into the Atlantic. And if you look right where that arrow is pointing, so that's the outer Cape, it's mostly Cape Cod National Seashore, so a lot of federal land in that area. And that's one of our main research partners on this project. So keep an eye on that arrow. It's pointing at this kind of bay on the left-hand side of the Cape. So we're zooming in there. This is our study site at Chequetsit Neck Road Dike. So it's on the bay side, the Cape Cod bay side of the peninsula. And as you'll see, the watershed of the Herring River goes up into the National Seashore. So this is a really good location for kind of collaborative research. There's a long, decades-long history of data here and interagency collaboration. And this dike across the mouth of the river, across the mouth of the estuary, is the infrastructure that we're going to be looking at. So this is basically a view looking upstream at the dike from the harbor and the bay. So this is an early 20th century piece of flood control infrastructure, basically dampening high tides, making them lower, but also making the low tides higher and just generally limiting tidal flow through that area. So this is previously a saltwater dominated estuary. As you saw in the previous image, the watershed is quite small. There's a lot of tidal flow in this area. And so this dike has transitioned this ecosystem over the course of a century to a freshwater dominated marsh that has a lot of water quality problems due to a lack of tidal flushing. It's also caused a lot of succession in the vegetation communities. So where there was once native salt marsh, there's now invasive freshwater marsh plants like Phragmites, as well as large stands of forest that have been established on top of former salt marshes. And now there's saltwater intrusion issues beginning with sea level rise, and some of those forests are dying. So as part of this restoration, they're going to have to do a lot of vegetation mitigation, which also relates to the carbon cycling piece, which is a central element we're helping to bring in with some of our model parameter inputs that we're hoping to provide. But effectively, this is a tidal restoration project that is going to replace this structure with an adjustable gate system that's going to allow a lot more water to move in and out of the estuary every day. and along with ecological restoration activities upstream, basically restore the former salt marshes here. So this construction has been planned for decades. It's going to actually start by the end of this year, we're told. So this is a really exciting time to do before and after research and look at how the flow conditions are changing here. But there are some really complex hydrodynamics at play that make IRQIV and just surface velocimetry in general a really exciting tool to apply here. So you have this complex two-way flow, and because of the restriction, the flow is not just dependent on current tidal conditions, but also the preceding tidal conditions. So this is just looking top down. At the previous slide, I'm not sure if you noticed on the last slide, there is water coming out of the dike. Here, the water's going into the dike. So you see this huge hydraulic head that builds up at high tides. And basically that is just forcing water at really high velocities through a very narrow constriction. So you'll notice there's 3 arrows on this slide. Those represent the 3 tidal gates that make up the dike. And you'll notice only one of them allows water in while all 3 allow them out. So this is a really complex situation that I kind of liken to 2 huge buckets of water connected with a straw that flows faster in one direction. And the upstream bucket inside the estuary can't ever empty out before the tide starts coming in again. So there's a really large tidal range. It's over 4 meters at spring tides, which is when we were out sampling. And again, that hydraulic head creates these really turbulent flows, and generally just an important opportunity for surface velocimetry to more accurately measure discharge in places that conventional acoustic methods and volumetric methods have not achieved adequate accuracy. So our main goal here is to help these 2 federal agencies, U.S. Geological Survey and the Park Service, to better parameterize their hydrodynamic model, which is coupled to a biogeochemical carbon cycle model, and help kind of direct the direction of the flow reintroduction by providing them with improved data. So here's what our field setup looks like. This is the FLIR infrared camera. You saw some images from it in Seth's talk. We put that inside of this large unwieldy metal enclosure to protect it from the rising tide. Overnight, when the camera was in this location, this is on the downstream side where you get the full tidal range. The tide actually went up to that first rung on the fence there. So ran all the electronics uphill, obviously. So yeah, it's a cooled infrared camera. We also had a visible light, full frame raw video camera, taking intermittent videos of turbulent aerated flow, trying to maybe learn something out of these aeration patterns that we're seeing in infrared that can be challenging. We also had an RTK system for georeferencing, and then had 2 different acoustic velocity instruments in the channel for comparison as well. So this pole, there's a pole, we got really lucky, mounted onto the dike on top of the 2-way gate on either side. And so this is what that pole looks like. And you'll be seeing images captured from that angle throughout the presentation. So this is basically a simulated field of view of the infrared images you're about to get a look at. The vertex obviously is the camera location. We started out with it mounted on a lower tripod, looking directly down onto, this is the upstream side of tide coming in. So all the tide's getting forced through that one gate coming in upstream. This was taken close to midday, midsummer. See really bright scattering of that solar radiation, and also a huge amount of air entrained in this. And as you can kind of see from the opening of the orifice all the way out through the field of view, the amount of air just qualitatively looks to be going down really rapidly, right? So if we look at what the image from the infrared looks like, you can see kind of these really bright features that appear and disappear. And some of this could be due to reflection. Some of it could be due to just bubbles bursting, or these turbulent features really rapidly moving on top of each other. And this is all the flow coming through basically a 2-meter wide gate into a quiescent upstream area that doesn't have a lot of its own velocity. So this is a challenging setting to measure discharge in as well. But the thesis here is kind of that these really rapidly appearing and disappearing features are going to be difficult for tracking algorithms. Excuse me. So now we've moved the camera up the pole. You're still looking at the same area from a higher vantage point, larger field of view. This was taken in the evening. The tide's still coming in. We get these really high velocities still forced through that one opening. All the tidal head is pushing water through really fast. The frame rate in these is a little variable. We were struggling with collection speed and just making sure our frame rate was consistent. So potential issue there when you have these really high velocities. As you'll see on the upper left side, you have this really still water, which actually has a surfactant layer on top of it that's sitting behind the two gates that are only flowing out. So that we're not really leveraging the whole field of view here. But what happens when the water turns around? So when the tide starts going out here, you get flow through all three gates, and we can see all the way across there. So really good coverage, and you get these very coherent thermal structures that obviously are changing quite quickly, but you can track them from frame to frame much more easily than the aerated flows, where you have some surface features that don't move and some that do. So everything's kind of moving together here, which we love to see. And this was taken in the early morning before the sun was up. So really helpful for the thermal infrared to be able to see in the dark. The spring tides we were sampling were around like midnight, 1 a.m. So being able to kind of sample the most extreme conditions, which take place overnight often in tidal systems, is really useful here. So now we're going to move back to the downstream side. So this is where the camera was mounted in that initial field setup slide. So once again, we see this really quickly changing intensity from the foam bubbles popping potentially. It really looks like fire dynamics to me, which is really interesting, kind of thinking about turbulence in that way. But basically, we're missing some flow here. So this pole on the downstream side is shorter. There's two gates basically to the north or up from this slide that we can't see. And again, these rapidly changing thermal patterns are going to be difficult for a tracking algorithm to hold on to when we're looking for something more coherent and changing maybe in space more than in intensity over the frames. So again, what happens when the tide turns around? Now we're looking at incoming tide going into the dike from the downstream side. And this looks really exciting. We have these coherent thermal structures. You can kind of visually track them, watch them move and accelerate and stretch into the opening. And again, those three gates, two of them only flow out. So we have all of our flow going in, as we saw from the upstream side. That can look very, very chaotic and turbulent, but on the downstream side, we really can see all these structures moving in together. So I thought we're just kind of beginning analysis here. We just collected this data in July, but I just wanted to run it through a very kind of lab scale PIV algorithm that was not even really modified at all for this. So just see what we get as a first pass. And so this is the vector field that I got just from the lab PIV code that we use in class. And it looks pretty good. So this is just a correlation approach, only tracking high intensity features. So basically only looking at half of the data, no georeferencing incorporated. But if we overlay that vector field onto the imagery, we qualitatively get pretty strong agreement there. So obviously we need georectification because we have these kind of artificial magnification of the near side versus the far side. If we're looking orthogonally, this would be we could assume to be roughly equal. And also, as Seth mentioned in his talk, MQD is a better method for infrared imagery where you have more subtle differences in pixel intensity compared to PIV or illuminated methods. So in the future, we're going to incorporate that. And just talking a little bit now about other directions for this project. So first of all, the whole point of applying IRQIV in this setting, at least from the agency's perspective, is to help them get a better value for Q. So we have this bathymetry data, and we're going to hopefully just take transects off of that right on either side of the dike, overlay that bathymetry onto the vector field or the flow field imagery, and then just derive surface velocities over a depth to get a first pass of discharge. This is a schematic of what the rebuild dike is going to look like. So again, construction is going to be starting. We have funding for at least 2 more seasons, hopefully 3. So by the end of that, I really hope that this construction is finished and we can basically help the agencies understand what the flow is doing at a given gate configuration. So I'm still wrapping my head around this a little bit, but I'm calling it a dynamic rating curve where you have variable infrastructure, a variable area that your flow is going through, and you're changing head through tidal stage. So basically set up the gates one way, watch a whole tidal cycle, extrapolate a rating curve, do it again, and just kind of help them hit their targets. There's a very complex plan for tidal restoration and decision trees and all those sorts of things. So providing better data through that process will really help the adaptation and the restoration process move forward. There's also obviously a huge vegetation component, which intersects with carbon cycle, which I'll be talking about now. So this is just an image from our lab of PIV experiment using a live plant, a milfoil in the flume. So you can see the illuminated particles as part of the experiment. And if you look at the vector field derived from that, we're going to hopefully apply this sort of method in the field now. So we've done vertical and horizontal PIV in the lab with vegetation, both simulated and actual vegetation here. We currently have a student in our group working on surface PIV through like a artificial mangrove forest. But now we want to see if we can take this into the field, because there's this process called lateral flux, which is basically carbon fixed in salt marshes, sediments, plants, etc., getting washed into the marine carbon cycle. So what we want to do is point a camera at the surface of the salt marsh after high tide while the water is draining through the marsh plants, and try and measure a discharge rate through that and measure velocities, and really see what we can do with the kind of loading rates or the per concentration values for carbon that the Park Service and USGS have collected, and see if we can extrapolate that to a flux out of the system. And the methane arrow here, I added that to this figure. That's basically another process we're looking at of direct flux from the marsh to the atmosphere. So that happens through ebullition or bubbling out of the water column. Degraded salt marshes can become pretty significant emitters of methane, and also parenchymus transport, so methane from the sediments going directly through plants into the atmosphere. So kind of as a holy grail in these images, this is a paper that one of the camera companies Seth was working with, Teleops. They worked with scientists in Sweden to basically help image methane directly out of a lake. So this is a very cool kind of holy grail or pie in the sky type of thing you can do with hyperspectral tools. So we're going to try and look at this maybe with a different camera down the road, but also we have this kind of expertise on surface turbulence and what you can extrapolate about bed stress and oxidation of gas transfer at the surface through that. So kind of two different ways, one very ambitious and one more based on the tools we're currently using to get at gas transfer. So I just want to thank Professor Cowan for helping me out in the field this summer, Atkinson Center for supporting this work, and National Park Service, USGS, Center for Coastal Studies, and thanks to Nick and Aisling and everyone who helped organize this. It's been cool to watch everyone's talks. And just to kind of conclude, so we got way better image quality on the upstream side for IRQIV because you kind of circumvent that aeration. We also saw really coherent thermal signatures. I think you get higher thermal gradients in tidal flows. So that can be a great place to apply IRQIV. And this is just a good example of where velocimetry can help kind of fill conventional measurement data gaps through agencies that have been working on this for a long time. There's still opportunities to help out there, and also intersections with the carbon cycle, both through direct imaging and inference through the hydraulics to gas transfer and things like that. And we're still interested in learning something from these aerated flows we measured. So we'll look at our acoustic data and our visible light data and kind of see what we can learn from the more challenging IRQIV images. So with that, I will take any questions.
Any questions from the floor?
That's a very interesting presentation. What was the scale on this color maps of the flow you showed in some of your slides?
Yeah, I had some, let me just go back here. I had rough, so I haven't done any georeferencing on these yet, but I have rough field of view parameters on here. So, sorry, let me just get it to play. So this one is like 6 meters by 3 meters.
Oh no, I'm talking about actually the temperature range.
Oh, the temperature. So this is actually unconverted. So we, I might get some pushback on this, but we generally don't need to convert to actual temperatures to see the patterns we want to see, right? So there's more of a calibration required to convert the pixel intensity that the sensor is receiving to an actual accurate temperature. So we're really just looking for differences in temperature, and the actual values don't don't matter as much. So this is what you're looking at is just raw pixel counts of how many photons are hitting the sensor in each integration period, and they're not converted to temperature. That is something we can do, but for purposes of pattern tracking, you just are looking for those differences.
Okay.
Thank you.
Any other questions? From the back?
Yeah, thank you for the presentation. You mentioned that you want to compute discharge from those velocity fields, and I was wondering how you will relate the surface velocity to the depth average velocity in such complex hydraulic conditions. I can expect that there are some 3D velocities and vertical velocities. So do you know how you will make the link between the surface and the depth average velocity?
Yeah, that's something that our group does have some experience in. I can't speak to the exact methods we'll use, but I mean, another nice thing about this system is all this water is just going through basically a culvert at the end of the day. So we'll look at the bathymetry and we'll see how far out we can kind of place that line. But as kind of a backup plan, we can just run it through the dimension of the culvert itself, kind of at the interface, like right at the entry point. So obviously, yeah, you do get some, you have your no slip boundary conditions at the bed, but in general, like Seth's talk showed, that you do get very good agreement between like an ADCP method and the IRQIV in many settings. So yeah, it's definitely something we'll have to look at, and that's also why we have the velocity, the acoustic instruments in the channel, and so we'll be comparing with those as well.
Okay, thanks, Evan. A very interesting talk. Thanks so much. Right, we want to move on to the final talk for the first day by Giulio Dolcetti, who's going to look at physics, space, and estimation of discharge. Hopefully, Giulio's still there.
Yeah, it is.
Yeah, do you hear me?
Hi, Giulio. Yeah.
Okay, let me share.
Sorry.
So, don't think, yeah, you see my screen now?
Yeah.
Okay. Just a second, try to, yes, okay. Well, hello everybody. I really wish I could be there, but I'm working in Italy now, but I hope it's very nice occasion for all of you. This work I've done when I was still at the University of Sheffield with Matthew Burks, Paul Balahotabagi from Newcastle University. It was done some time ago. It took a bit longer than we wanted to finish writing it and submit it, but it was published just a few weeks ago, so this is quite timely. And I don't know if somebody's there from the Environment Agency, but I would really like to thank them because they did a lot of work in helping us, sharing data, helping set up the instrumentation. So really thanks to all of them. So the motivation behind this work, we wanted to see if we could somehow deal with some of the limitations of some of the surface velocimetry methods. Namely, the fact that in order to have good accuracy, generally, it's necessary to have very high density of tracers, and that accuracy also reduces in the presence of water waves. So we've done some work on trying to highlight what is the effect of water waves and the fact that they move at a different velocity. We saw the effect of standing waves on the stability in the accuracy of the data. And in general, I would always recommend not to use things like LSBIV in case there are not tracers. But the other limitation is that for most surface velocimetry methods, we need to know the depth, we need to know the bathymetry, and also we need ways to convert from surface velocity to depth average velocity. So this is everything that we try to cope with. We didn't manage to do all of it, but at least some of these things we managed to hopefully do something about. And the way we approached the problem was based on what we've done in the future. So we've done, as a group, a lot of work in trying to establish what is the behavior of the water surface and how that links to the conditions of the flow. And we mostly came to the conclusion that there are different types of patterns on the free surface. Some of them are clearly seen as gravity waves. Others are clearly caused by the interaction with turbulence, boils, vortices. But most of the times, or many times, it's not so easy to distinguish which is which and what is causing the things that we see. So a tool that I used a lot is fully transform, is basically what is called the frequency wave number spectrum. So it's a fully transformed, not just in time, but also in space. So instead of just distributing the energy of a signal in terms of the frequency, it distributes it across frequency and wave number, which is a spatial frequency. It's the inverse of a wavelength. And this kind of approach is useful in the sense that by taking the ratio of the frequency and wave number, we can find the speed of each wave that is present at the same time on the surface. So it allows us to distinguish the gravity waves, which velocity depend on their wavelength, from other structures. And what we wanted to do, and this was actually fairly new in terms of applications in rivers. There's very, very few works that try to do similar things, but it's a very established method in oceanography. So there are works that date back to the 1940s that they try to use the dynamics of the surface to estimate the conditions of the flow and everything that lies beneath the free surface. So basically, we start with a simple model, hydraulic model. In this case, we use this linear profile, so the black line, which shows that velocity is estimated to vary linearly across the flow. And this profile is defined by only 3 parameters, which are the velocity at the water surface, the depth, and the slope of this profile. So, and then based on this model, we can predict what the dynamics of the free surface will be. We can predict what the speed of the gravity waves is going to be for these parameters. And we can see how those change with the flow conditions. So if we increase the surface velocity, for instance, sorry, didn't mean that, okay. We see in the center top, we see that the frequency is increasing for the waves that are moving downstream. It's decreasing for those that are moving upstream, but we see a clear change in these lines, in this behavior. There is also a difference in terms of depth, although it's a lot weaker, a lot more subtle. But basically, if we can see these differences in the data, then we can use this information to estimate these parameters of the flow, so the depth, velocity, and that shear rate. In practice, no matter how hard I tried, but I never managed to reconstruct the 3 parameters at the same time. So instead, what we did was to link the slope of this, or the velocity profile, to velocity index, and then assume a certain value for that velocity index. And we picked 0.83 following some recommendation in a paper by Alex Hoy. So let's see basically how it works. So we start, as we said, we don't use tracers. So what we see is the deformation of the water surface. That is what we try to use. And the way we see and the way we can measure the deformation of the water surface is based on 2 phenomena. The first one is the so-called sky gradient. So the color of the sky that changes and becomes lighter near the horizon. And then the fact that the reflectivity of the water also changes with the angle. So we have basically all the light is reflected at grazing angle, whereas some light passes through the water surface if we look at it from directly above. So because of these 2 effects combined, when we take a picture of the surface of a river, which we see a pattern of pixel intensity, which relates to the slope of the surface. And that we can use as essentially a measure of the surface slope, and this is related directly to the actual surface elevation as well. So we can use that directly. And then we do things which are very common for many surface velocimetry data. So we rectify the images, we extract a window. And then we have collections of these images taken at different times. So we have a 3D block of data, and we take a Fourier transform in the 3 directions. So we end up with a 3D spectrum in the 2 directions in space and 1 direction in time. And here I'm showing some cross sections through this data set. And then we compare the measured spectrum at the top left and right here in the 2 directions with the synthetic, the ideal, the theoretical spectrum, which is calculated for given values of the parameters that we want to estimate. So in this case, the depth and the velocity. And then we use some optimization algorithm. We used a genetic algorithm in this case, but other methods could be used equally well. And we look for the best fitting between our prediction and the actual measurements. And based on that, we estimate the depth potentially and the velocity. So of course, there are some uncertainties. The first one is due, like I said, to the fact that we have to pick a value of the velocity index without really knowing which one is the correct one. And if we change the velocity index, we are changing slightly the shape of the theoretical spectrum. So even the parameters of depth and velocity will have to accommodate that change and will change slightly. So that introduces some uncertainty, which for typical values of the velocity index alpha between 0.7 and 0.9 is 5–10%. But then there is an even bigger source of uncertainty, which is due to the fact that when we compute, we use the velocity and depth to estimate the discharge, then we introduce a direct dependency on the velocity coefficient, and that increases the uncertainty to, let's say, 15% in this case. And then the other source of uncertainty, which perhaps is the most important from what we saw for this method, is due to the fact that, like I showed earlier, the dependence on flow velocity is quite strong, but there is very little effect of the flow depth on the dynamics of the water surface. So in order to be able to measure this very small difference, we need very good spectral resolution, which typically means we need a very big window. So on the right, I'm showing the sensitivity to velocity and depth. Left-hand side are very long waves and right-hand side are very short waves. So the sensitivity depends on the size of the waves. And for sensitivity, it tends to be relatively high, especially if the waves are short. For the depth, it is lower, and it has a peak for waves that have a wavelength of about 6 times 2 pi times the water depth. So the waves that the information, the part of the surface that carries most of the information about the water depth is limited to some fairly long waves with a wavelength of about 6 times the depth. But we also need to be able to measure these waves accurately. So we need a window which is bigger than that. So the window size has to be bigger than the water depth. So here I show I'm showing what I mean. So these are 2 images taken from the same river, the river sheath, at different times. So that the discharge was a lot different, 0.87 versus 5 cubic meters per second. And we see clearly a strong difference in terms of the behavior, the shape of the water surface and the scales. So we can see it in the rectified images as well. Lambda naught there indicates the predicted characteristic size of the surface. In the paper, we discuss a bit better how to calculate this. But we see a difference, and the bigger waves are found at the faster flow. That's something we can expect and we can predict. That means that we're going to have the ratio between the size of these waves and the size of the window is going to be bigger for the flows with a higher velocity. So we expect bigger uncertainties at higher velocity. In this case, also it meant that you can see the bank of the river basically at the top of this image on the right. So in this case, the window had to be so big that it basically covered most of the width of the channel. So for all this work, we had to resort to picking just a single point, a single window that covered most of the river size, and that would only give us a single measurement of the depth and of the velocity, which we take as the average values of the depth and velocity, and then from those we would estimate a discharge. We've done tests in 2 rivers, the River Sheaf and River Calder, with a large wide range of flow conditions. So the discharge varied by 1 order of magnitude and more even. And we took measurements at different times of the day, different days, to have wide range of conditions, also of illumination conditions. And these are the results. So on the left, we see the estimated depth against the measured one for the River Sheaf in red and the Calder in green. The perfect reconstruction would be the dashed dotted line. And we see the uncertainties there, which we calculated. Those are only the uncertainty due to the limited spectral resolution of the method. So they are bigger for the higher flows for the reasons that I mentioned earlier. And then in the center, we see the estimated discharge in red compared to some gauges, ADCP gauges in black, and the rating curve for the River Sheaf in the center and for the Calder on the right. So in general, I would say that the measurements were within the expected uncertainty, which is always reassuring. And this is just to show how we capture different peaks and how the flow changed in time as well for the times when we were taking all these measurements. So this was basically what we showed in the paper. As I said, the main the area where there is more room to improvement is probably the resolution, and there are perhaps ways to increase that. But that is mainly due to the fact that the uncertainty of the depth would be quite large because of the low sensitivity. So if instead we knew already what the depth was, we knew the bathymetry, then we could reconstruct only the velocity with a much smaller window, and then potentially also reconstruct the whole transect. So these are examples of doing exactly that with the same method, but only for the velocity. And these were taken from a benchmark test that was done in 2020 during the pandemic. So these are the videos that I analyzed. And I don't know if somebody has the final score for that thing, but here I'm comparing how the percentage error varied for the different data sets that were analyzed there compared to other methods such as SPIV, PTV, STIV. So it was within the same range of uncertainty, but somehow with the benefit that in our case, although here there were traces, but the method itself wouldn't need traces, but could also work even just with gravity waves and in a physics-based method. And to conclude, you've seen Kirill and Michael's presentations earlier. Kirill especially showed how to reconstruct the frequency wave number spectra of the water surface using sound. So the method would apply to that kind of data just as well. So potentially we could use acoustic data to reconstruct the discharge in a very similar way to what I just showed. That is it. So these are the information about the paper. If somebody's interested, or just contact me, and I'll be happy to have a chat about it, and I'll take any questions.
Any questions from the audience?
Use processing time.
Sorry, Julie, processing time?
It depends on the size, of course, and on the resolution of the images. So most of the times I had to downsample the images because the resolution was higher than what we actually needed. It's important to have long videos because then the uncertainty decreases a lot. So I got the best results with videos which were about 1 minute long. then measuring the spectrum would take, calculating the spectrum with my PC would take a few minutes, let's say less than 5 minutes. And the optimization, depending on the size, but it would be 15-20 minutes, let's say. So half an hour, basically, is the amount of time it took for my computer with this analysis for a single measurement.
Any other questions from the audience?
Hi, Julio. Good to hear from you.
Hello.
Hi. Yeah.
Oh, hi, Nick. Sorry. Now I see. Okay.
Yeah. Okay. Yeah. The site at Todmorden is very narrow. Would that have an influence? You know, would the sides be having an impact on the surface structure as much as the bed and the velocity profile?
The bigger the river, the better it is, because of this. So we need a window which is reasonably big, and in Todmorden, I couldn't actually have a window which was bigger because of these. The waves were longer than the actual size of the river. So I had to take a rectangular window instead of the square one. And the reason why here the uncertainties are bigger for the Todmorden is exactly due to the fact that the width didn't allow a big enough window. So in that sense, yes.
So is it just the width though, or is it, you know, my concern was that some of those features might be created by the walls of the channel because it's so narrow?
Even if it was, it wouldn't be. So the origin, what causes the waves doesn't matter. It could be a bridge pier, it could be a drain, it could be someone paddling a boat or a boulder. It doesn't matter because waves would still follow that behavior. Unless, so that there are conditions where maybe that would fail, and that is if the waves become very steep and then there are some nonlinearities. But there could also be ways to cope with that, even in that case. But in general, it doesn't matter if it's wind or what is causing the waves.
Okay, all right, thanks. And it's good to see those sites are still there. I remember them going in.
Okay, any last question? Oh, one.
Hi, Julio.
Hello.
I was wondering, considering the large region of interest that you need to have to your computation, do you need to have like homogeneous velocities in this area, or can you have gradients of velocities?
In principle, yes. We assume that everything within that window is homogeneous. In practice, when we take the spectrum, we combine the information for all the waves that are within that region. For instance, the waves that give us the information about the depth, they're pretty long waves, so they wouldn't be so much affected by changes in the flow conditions in across a distance which is smaller than the wavelength. For velocity, it could be an issue. So potentially one could combine a higher resolution velocity using smaller windows with a bigger window for the depth. That is possible. And there are, of course, some issues at the if there is a sharp change of the velocity. But if you can see here, for example, there was a recirculation zone, and we still managed to capture it pretty well, I would say. So it could be an issue, but probably the same as it could be for LSPIV, I believe.
Yeah, thank you.
Thank you.
Thank you, Julio. Oh, one last final question, sorry.
Thank you, Julio. That's really interesting. Just one question: how will your method handle the shadows, for example, or static optical patterns at the surface?
I do the trending, so I remove everything which is constant, And then everything which you see it here. So everything that moves with a very low frequency appears in this part of the spectrum here. So it's easily removed from the optimization and from the fitting. The advantage, the fact that the method is physics-based is that we can easily remove everything which is not physical. So we can separate everything that seems to be traveling too fast than is possible or too slow.
Okay, great, really interesting. Thank you.
Thank you.
Thanks, Julio. I think that's the questions finished.
Thank you.
Appreciate it's been a long afternoon. We've still got the 4 speakers online, or the 4 speakers still here. So are there any final questions that anybody would like to ask for any of the speakers? Okay, thanks very much for your attention this afternoon. So let's I think the organization for tomorrow is 9 o'clock here. I think so, yeah. And where Rick will tell us what we're going to be doing for the rest of the day.
Yeah.
And thanks to Joe for keeping good tab of what's happening.
Yeah. Yeah, thanks, John, for keeping us on the straight and narrow in our